Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to just demonstrate how to calculate potentials in a uniform electric field. And again, this is going to be kind of the simplest type of case here, uniform electric field. Usually electric fields vary with distance, but we're going to start with this. And we're going to assume in this example we've got a 10 Newton per Coulomb field, uniform everywhere in this picture. So if I pick a spot here, 10 Newton per Coulomb to the right, here 10 Newton per Coulomb to the right, here 10 Newton per Coulomb to the right. And what we're going to do here is we're going to calculate the electric potential at the following locations: 0, 0, point B here is at 3, 0, point C is at the point 2, 4, and point D minus 1, 0. Assuming at x equals 0, the electric potential is defined to be 0. So meaning that we're putting a datum here in this problem. So I'm going to go ahead and put that datum in first. Now, electric potential is an energy concept, and again, it's related to potential energy. And just like in a potential energy problem, remember, you can always define a datum for a potential energy. You can do the same thing for potential. So we're going to define the electric potential to be 0 anywhere along this actually surface. I'll probably say line in the video because it's a line on my page, but you have to remember this is actually like a surface coming at you, because if you come towards yourself a little bit, the potential doesn't change. Remember, to change in potential, you have to move either with the electric field or against it. All right, anytime we move this way or this way in this problem, there'd be no changes in potential. All right, so potential difference, when you calculate it, potential difference is calculated by field strength times distance. But it's important to recognize that the distance and the field strength you use, they have to be parallel to one another. So taking these one at a time, the potential, well, we'll start with the potential at A. A is at the location we have defined as our datum. So I'll just write this over here. Potential A would be 0 in this picture. Now we'll work on potential B. The difference in potential between here and here is going to equal the field strength, 10 newtons per coulomb, times the distance, which would be 3 meters in this example. So we're going to get 30 Newton meter per coulomb, or 30 volts. I'll write 30 joule per coulomb. Now when I do potential differences, I usually do magnitude first, and then I attach a plus or minus sign based on did we drop in potential or increase in potential? If you move from A to B, we're moving with the field. So that's going to drop us in potential by 30 volts. So I'm going to go ahead and supply a minus sign for that. So potential B, right, we're starting at 0 and we're dropping by 30 volts. So potential B would be minus 30 volts, or minus 30 joule per coulomb. Let's work on D, and then we'll do C. All right, now I'm going to kind of compare A and D. Now, the distance here between A and D, 1 meter, because this is at the point minus 1, 0. So the potential difference now between A and D, we're going to have 10 Newton per Coulomb times 1 meter, and out comes 10 joule per coulomb, or 10 Newton meter per coulomb. A Newton meter is a coulomb. I'm sorry, Newton meter is a joule. Now, the electric field points to the right. As I move from A to D, we are moving against the field. We're moving towards higher potential. So this represents an increase in potential difference. So the potential at this point, D, would be plus 10 joule per coulomb. Now we're going to imagine, or try to calculate, potential difference between A and C. Now there's a couple ways to kind of imagine this. Method number one, as I move from A to C, you can imagine moving up to this location and then this location. There is no potential difference when we go from here to here, because this is an equipotential. Then we would drop in potential by an amount 10 times this distance, 2. So the potential difference between this point and this point is 10 Newton per Coulomb, and that distance is 2 meters. All right, so our numerical value, minus 20 joule per coulomb. I'm sorry, 20 joule per coulomb. And the minus sign, which I'll kind of insert here and here, is because we're moving with the field, dropping in potential. So potential C, starting at 0 and then dropping by 20, is equal to minus 20 joule per coulomb. Now, I said there's two ways to think about it. That's one of them. Imagine going from A to this point right here. There'd be no change in potential. Then imagine going from here to here. You would drop in potential by 20 joule per coulomb. The other way we could think about it is just imagine, I'm going to draw this vector in blue. Imagine a displacement vector, like a change in position. Starts at A and then moves over to B. That is a change in position, a delta, let's say delta R. I use R for position vectors a lot. Delta R is 2I plus 4J in using unit vectors in meters, because it's 2 to the right and 4 up. We could also calculate the difference in potential. I'm going to put the A and C on here, so between A and C, by taking this distance and multiplying by the 10 newtons per coulomb. So 10 newton per coulomb times 2 meters. And I would be getting the 2 in this case by taking the component of the displacement that's in the direction of the electric field. Right? And then I'm going to go ahead and attach a minus sign for the fact that that component is to the right. We're moving with the electric field. And again, we get minus 20 joule per coulomb. So here's some examples of calculating potential differences. And I've also actually calculated numerical values for a potential based on the fact that I set a datum here. Now, some things I'd like to point out. If we go from, let's say, C to D, or I'm sorry, D to C, D is at a potential of 10. C is at a potential of minus 20. So if we go from D to C, we're going to drop in potential by 30 joule per coulomb. Let me write that out. Change in potential between D and C is going to be minus 30 joule per coulomb. And again, look at why. If I draw the equipotential through D, here we are, and I draw an equipotential through C, right through all my work here, this potential right here, according to this datum, is plus 10 joule per coulomb. That would be good anywhere on the green. This potential, again relative to this datum, is minus 20. So if I start here and end here, we're going to drop by 30 joule per coulomb. What I'd like to point out is, imagine for a minute I put the datum here and think about how these would change. This would now be the zero potential. When we calculate 10 times this distance, now it's 1 from here to here, 2 from here to here, so that distance is 3, we would drop in potential by an amount 30 joule per coulomb. The difference in potential between D and C does not depend on where the datum is. I can put this 0 anywhere I want. I can put it here, 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 or over at B, and the difference in potential between D and C is going to be minus 30 joule per coulomb. And that's why we can put the datum anywhere we want. The only thing that ever matters are differences in potential. Right? The actual values like this plus 10 here, this depends on where I define my datum. This is not a number that really matters. The only thing that ever matters are differences in potential, and that's an important fact when you're dealing with potentials. So anyway, this video was meant to just give you an idea of how to calculate potential differences and how to assign values of potential once you set a datum. I hope that it's effectively done that for you. Have a great day.